these expressions for little r and little t are called the Fresnel equations. So we've actually only derived one, which was the reflection coefficient for TE, and I gave you another one, reflection coefficient for TM. Let's apply it to an external reflection and see what it says. So external reflection means basically how we set this up is that you're in a low index on the outside and you're at the boundary to a higher index. So we've been describing this just by saying outside is just 1, it's just vacuum, and the interface is going into a higher index medium like glass, where it might be 1.5. So that's what we mean by external reflection. You can imagine what may be coming is one from the inside, but for now, external means from you're leaving a low index medium and going into a higher index medium. So we know we have written this. We said that, well, we care about the reflected field, and we know it's a little r times the incident field, and we calculate a little r. So let's look at a plot of little r and see how it looks. And here it is. So we plotted it here from both expressions, one for Tm and one for Te, and I'm plotting it for n equals 1.5. So we're doing it basically for the air-glass interface, and we're looking at it for all angles. So you'll notice both Te and Tm come to about the same value at normal incidence, at theta equals 0, of about minus 0.2.
Wait, what? Clearly on our plot, Te is negative 0.2, but Tm is positive 0.2. As the explanation continues, I show the two expressions for the reflection coefficients for Te and Tm, and we decide that at normal incidence they're the same, negative 0.2. So is this plot a mistake? Well, sort of. Remember in the prior lecture that when we derived the Te reflection coefficient, I said, let's assume the reflected field points down. I could also have chosen it to point up. Whether the reflected field points up or down is a difference in phase of pi, which for sinusoids is like multiplying by negative 1. So whether you'll get a positive or a negative reflection coefficient depends on your guess for the reflected field direction. But in the end, it won't affect your physical result, it just affects the math. So when I derived that expression for Tm, I chose the reflected field to point in a way that makes both reflection coefficients give negative 0.2 at normal incidence. But when I made the plot, I grabbed the formula that assumed the field went the other way for Tm, and that's what's shown. The plot that matches our expression should have both coefficients at negative 0.2 at normal incidence, and then diverge to plus and minus 1 for glancing incidence at 90 degrees. You'll see both versions of the plots and expressions in different optics textbooks. Also, as we move forward, we'll look at irradiance, which is proportional to these coefficients squared. The plots I show are correct because it doesn't matter which way you go since the coefficient gets squared anyway. Note that in both cases, the one I showed here and what the plot should have looked like, only the Tm reflection coefficient goes through 0, so both cases would also predict the polarization effects we're going to talk about soon. Okay, back to the lecture.
So let's see if that makes sense. Here, let's see. So at theta equals 0, cosine of 0 is 1, and sine of 0 is 0. So this is 1 minus square root of n squared. So 1 minus n on the top, and 1 plus n in the bottom. 1 minus n over 1 plus n. Tm is minus n squared plus n over n squared plus n. Well, that actually is the same thing. If you cancel an n out of this, you get minus n plus 1 over n plus 1. And minus n plus 1 is the same as 1 minus n. You just turn it around. So they actually give you the same thing. And they even give you the right value, 1 minus n. Well, 1 minus, and if we're doing glass, that's about 1.5 over 1 plus 1.5 is about minus 0.5 over 2.5, which is about minus 0.2. So at normal incidence, we do get about the right thing. Okay. And then, as you go off to glancing incidence, they diverge. One goes up to 1, and one goes to minus 1. And what that means is you get a really strong field. You get the full amplitude of the field. One flips its phase, and one doesn't. In one, the amplitude peak is the same as the incident, and one, well, for Tm, the reflected E field is the exact same direction as the incident, and for Te, it flips. Okay. So that's kind of what we get out of that coefficient, but it's not too useful because we can't see the electric field. You don't directly observe the electric field, especially for light where it's going at 10 to the 15 hertz or so. It's kind of hard to keep up with. What you really see is the irradiance. Right? This is the reflection coefficient that applies to the electric field. So let's write this as for fields. And say we now understand that. But the irradiance is what you really see. And the irradiance, remember, is EE. So we're going to stick with this notation, EE. We may change it later for something else, but for now, we're stuck with it. The irradiance, EE, for the reflection. So before we said the irradiance was 1/2 epsilon naught c squared E magnitude times B magnitude, or amplitude times B amplitude, when we did the time average and everything. Now we just want to talk about E, so we're going to replace that B with an E over C. It's going to cancel one of the C squareds down to a C. Okay, so just hang in there with me. It's 1/2 epsilon naught C times the reflection amplitude, E naught R squared, as we sort of defined it earlier. Okay, but we could write that in terms of the incident amplitude. We could say, oh no, it's 1/2 epsilon naught C times R squared E naught I squared. We could write it that way. So you see, to get from fields to irradiances, you basically square the field magnitude. So to get this effectively the same thing in terms of irradiance, in terms of actual watts that you see, we call it big R. We basically just have to square it. But then we have a new name for it. If we have E reflected, we say that's equal to R squared E incident. Okay. Because if we wanted to get this ratio, we'd bring it under and all this epsilon naught C stuff would cancel. And really the ratio of the two irradiances is just big R squared, or just big, oh my God, it's just big R. There you go, is big R. And this is for irradiance, where big R is called the reflectance. And it's equal to little r squared. Okay? So little r is for field, big R is for irradiance and for power. So let's look at a plot of what big R looks like. And here it is. So big R also for TE and TM as a function of angle. So if we look, we can see some interesting things. One is that little r of 0.2 or minus 0.2 squares to about 0.04. So at normal incidence, you get about 4% reflection. So big R, if you multiply by 100, you get a percent reflection. So if I take a piece of glass, this is my dielectric, it's got a nice flat surface, and if you look at it, you've probably noticed you kind of see a ghostly image of yourself in a piece of glass. You do get some reflection, and here you're getting the 4% reflection. If you hold it against a dark background, you can get a good mirror effect. You can kind of see the 4% of the light if you don't have a lot of light coming through. And if you hold it against something bright, you can't see it at all. So bare glass can kind of make a mirror. One interesting thing though now, if we continue to look, if we go to high angle of incidence, the little r's both went to 1, you square that, and the reflectances also go to 1. So a mirror, or I'm sorry, a piece of glass actually makes a good mirror at a high angle of incidence. So and you can't, unfortunately, ever look at yourself that way. Or selfie generation just doesn't work out, because if you turn it at a high angle of incidence where you get a good reflection, you can't see yourself anymore. But here I can do it in the camera. So here I can see you in the close-up camera, and I'm going to bring this to the side, and I'm going to look in and make it a good mirror to see you by holding it at a very steep angle. So here I'm looking right at you in my good 80 degree, 85 degree piece of glass. And then I'll look at the camera, the glass, camera, glass, camera, glass, camera, glass. Right? So it makes a good mirror from the side. You just can't look at yourself, unfortunately. So, there's one other very important point in this plot. And you may have noticed, if you're looking carefully at the little r, a big difference between them is that Tm goes through 0 and Te never does. Right? Te is negative, but it's always got a value. Tm crosses 0. That means when we square it, there's a little dip where Tm, the reflectance, goes to 0. Right? So Te goes from 4% to 100%. Tm also 4 to 100, but Tm takes this little diverging path here. at an angle of about 56 degrees to give you nothing. What this means is, for a dielectric surface at a certain angle, it only reflects one polarization. Okay? It's called the polarizing angle.